Alright, hello. Today we'll be doing FRQ number 2. So, first part asks for an expression for speed of either star. So, first off, I'm going to set FC is equal to f of g, and then I can expand that out. So, mv squared over r, which is from pivot to center of mass of the object, and this is g m over d squared. D is the distance from object to object, and so one of these m's can cancel, and then I'm going to rearrange the equation to isolate for v squared. So gmr over d squared, but then I know that d is the diameter, so it's just 2 times the radius, so gmr over 2r squared, which is equal to gmr over 4r squared. One of the r's will cancel, so then I get that v squared equals gm over 4r. Radical of that, so I get that v equals rad gm over 4r, or pull out the 1/2, or the 4, which is 1/2, so gm over r. So that's part A. Part B asks for an expression for the time period. So using the from the last question, I know that v equals radical g m over 4r, but then I also know that v equals 2 pi r over t, which is coming from circumference over time, so I can set them equal. So 2 pi r over t is equal to radical g m over 4r. I'm gonna square both sides to get rid of the radical, so I'm gonna get 4 pi squared r squared over t squared is equal to gm over 4r. And so now I can isolate for t squared, so I'm gonna move the 4r up, so it's just 16 pi squared r cubed over gm, because I moved that down, and I move the t squared to the other side like this. I take the square root of both sides, so I get that t is equal to 4 pi radical r cubed over gm. That's part B. Alright, so now for part C, it's asking for total energy in the system, so I know that it's going to be equal to the potential, or the kinetic energy of one mass plus the kinetic energy of the other mass plus the gravitational potential energy. So I can expand this out, so 1/2 mv squared half minus gmm over d, and then I know that the first two terms can combine, so it's just going to be mv squared, but then I know that d is equal to 2r, so we do that right now. But then I also know that the v we found earlier was v squared is equal to gm over 4r. So but then I want to have a common term, or a common denominator, so I can just multiply by 2 over 2. So 4r minus 2, which is equal to negative g. That's the kinetic, or that's the total energy of the system right here. Alright, so now I'm going to go into part D, which is asking for the angular momentum of the system. So now angular momentum can be expressed as CPR, but there's two masses, so I got to do that twice. But then the C's will cancel because the mass is just point mass in this case. So I know the P, which is momentum, can be expanded to mvr plus mvr, which is equal to 2mvr. But I know that in an earlier part of the FRQ we found that v is equal to 1/2 radical gm over r, so I can plug that in. So 2m 1/2 radical gm over r times r, 1/2 will cancel, so I get L is equal to r m radical gm over r. But then I can put the r m inside by putting them under and making both these squared and multiply them together, so it's just going to be gm cubed r squared over r, so this r will cancel with that, so angular momentum is equal to radical gm cubed r, and then it's negative because it's going clockwise, so the angular momentum is negative in this case. And then for part E, it's asking to draw a diagram of the orbits if one of the mass is 3 m's now. So I'm gonna set this up here. This is box. So this is 3m. I'm gonna say. Let me say this is m. So I gotta find the new center of mass, find out what it orbits around. So I'm gonna do it from the 3 meters or 3m because it's a little bit easier. So I'm gonna say md over m total. So it's just md over 3m plus m. So md over 4m. So d over 4. So xm is d over 4 from here. So I'm gonna say that's about like right there, which is a fourth of the distance away. So the orbit around that for the 3m would be something like this. And the orbit for the other m, that's just the 1m, it will be much bigger, like far around like that. And that should be it for part E. Alright, so now we're going on to part F, which is asking for the angular speed of the 3m mass. So first off, I'm going to set FC equals FG. And then this time I'm going to set 3m AC is equal to gm 3m over d squared. And the 3m will cancel out with that 3m, so I get AC. But then AC I know is r omega squared. This is for the 3m. And then over here, d squared. But then I know that finding the XCM for the 3m mass, again, I know that from the last part it was d over 4. So that's the XCM from the 3m mass. So that's the radius for here. So I know this is d over 4 omega squared is equal to gm over d squared. So then I'm going to move that over, so isolate for omega. So omega squared is equal to 4gm over d cubed. But then the r that they're asking for is going to be half the distance. So that means it's just going to be 4gm over 2 big R cubed. And so this is equal to 4gm over 8r cubed. This cancels with that. So we're just going to make omega squared is equal to gm over 2r cubed. The square root of that. So I get omega is equal to rad gm over 2r cubed. That's it for part F. Alright, so now I'm going to move into part G. And it's asking if the claim is true or false. And the claim is actually false because t is equal to 2 pi over omega. But then omega is the same in a binary star system for both masses. So it means that t has to be equal to the same. So it's false. Very simple for G. Alright, so now going on to part H, it's asking if the time period of the new system has changed, decreased, stays the same, or increased. So first off, t new system is equal to 2 pi over omega, but then I know that the omega that we found for the new system was radical gm over 2r cubed. So radical gm over 2r cubed. But then I gotta flip that reciprocal, so I can just write this as 2 pi radical 2r cubed over gm, or say that t new equals 2 rad 2 pi times r cubed over gm. But then I know that the t original that we found earlier in the question was equal to 4 pi radical r cubed over gm. And then just looking at it, you know that t original is bigger than t new because of the coefficient in the front. So then I know that the t has actually decreased. That's the answer for part H. Alright, so now I'm gonna do part I. So first off, the gateway function v equals r omega, and so v over r equals omega. And but then so we can set that up, so v3m over r3m, and then at the same time we're going to set up again equals omega. And since omega is the same for both, we set them equal to each other. So V3m for R3m equals Vm over Rm. And so if I want to find the ratio, I divide. So V3m over Vm is equal to R3m over Rm. But then from the earlier part, we found that the XCM, or the radius in this case, of the 3m was d over 4. So but then if one of the radiuses is d over 4, the total distance minus is equal to r of the other m, which is equal to 3 over 4. So simplifying that down, d over 4 multiplied by reciprocal, d cancels, 4 cancels, so it's equal to 1 over 3. That's it for part I. Alright, so now for part J, I was going to compare the angular momentums. So, you know that angular momentum is equal to I omega, so I'm going to set up for 3m first. So, I can be expanded out to mr squared, so I'm going to say 3mr, and then 3m. But then before we found that the r of the 3m was d over 4. So this is just 3m d squared over 16 omega. And then for the other one, this is just going to be m, like that. And so r of the m we found before again is 3d over 4. So this is just going to be equal to m 9d squared over 16 omega. And so they asked for L3m over L3m over Lm, and so put them on top of each other. So 3m d squared omega over 16 divided by 9md squared omega over 16. This cancels, d squared cancels, omega cancels, and then the 16 cancels. It's just left with 3 over 9, or aka 1 over 3 once again. Alright, so now going on to part K is asking to compare the momentum of 3m to L system. So I know that L3m from the last part was 3 over 16 md squared omega squared, and then L system is just equal to L3m plus Lm. So then if I add them up, I get that it's going to be 3 over 16 md squared omega squared plus over there is 9 over 16 md squared omega squared, so it's 12 over 16 d squared omega squared. So then I know L3m over L sys, so this is going to be 3 over 16 md squared omega squared over 12 over 16 md squared omega squared. M's cancel, d's cancel, omegas cancel, 16's cancel. So you're left with 3 over 12, which is equal to 1 over 4, which is the answer. Alright, so for the very last part, it's asking to compare the kinetic energies of m over 3m. So first off, I need to find the velocity. So v equals r omega. So I can find the velocity of the first mass, which is r m omega. So this is equal to, before we found it was 3d over 4 omega. And then for the other one, so it's r3m omega. So this is d over 4, like we found before, omega. So now that we have the velocities, we can set up k. So k equals 1/2 mv squared. So for k of just m, I can do 1/2 m, and then v we found right there is just 3d over 4 omega squared. And then for this one, K3M, so 1 half 3M, and then inside D over 4 omega squared. So I'm going to simplify this a little bit. So this is 1 half M 9D squared omega squared over 16. And on this side it's K 3 over 2M times D squared omega squared over 16. So now just put them on top of each other. So M Km over Km. So this is 1 half. So it's 9 over 2 M D squared omega squared over 16. All of this is over 3 over 2 M D squared omega squared over 16. So M cancels, D squared cancels, omega squared cancels, 16 cancels, the 2's cancel, so just left with 9 over 3, which is equal to 3. That's it. Thank you for watching this FRQ video. Hopefully I did everything correctly, and have a good day.